Hello, in this video I want to solve a very simple thermodynamic problem, a problem that involves evaluation of properties of a gas manually and then verify the manual calculation using TESTcalc. And I want to show how use of TESTcalc not only gives us confidence but also how it can enhance our understanding of a problem. Okay, so here is the problem. It involves a tank of gas, a cylinder of gas that contains hydrogen. And essentially we are heating it from an initial state of, the initial condition is given 20 degrees Celsius and to a final temperature of 200 degrees Celsius. We are asked to find the change in pressure, the change in stored energy, and change in entropy of the system. Okay. The manual solution is pretty straightforward. We understand we can use the ideal gas equation of state. If I apply that equation, PV equals nRT, or mass over molar mass RT, or m R bar over m bar T, which is also known as MRT. So if I use the ideal gas equation of state, very well-known equation of state, I can figure out the pressure at state 1 and state 2. So let's do that. So PV equals P1 V1 equals MR T1. That leads us to P1 equals m over v. Actually, I don't have to write, volume doesn't change in this problem. 8.314 is the molar mass, universal gas constant. 2 is 273 plus 20. 20 is the initial temperature. And that turns out to be, that gives us, if I substitute, mass equals 1 kilogram and volume equals 2, so this becomes half. 8.314 by 2 times 293, and that turns out to be, I think I calculated that, 609 kPa. Likewise, we can find P2 would be the same mass, same volume, R bar over M bar, T2, and that's mass is 1 kg, 2 meter cube, universal gas constant, molar mass, and 273 plus 200, so many Kelvin. And that P2 becomes equals 983. So that gives us our delta P. The first question is find delta P. 983 minus 609, and that's equal to 374 kPa. So we got our first answer. To find the change in stored energy of the system, delta E is delta U plus delta KE plus delta PE, because we know stored energy is sum of U plus KE plus PE. There is no change in kinetic energy, no change in PE. So the equation simplifies to M times change in specific internal energy. So it's M for an ideal gas, for a perfect gas. The formula simplifies. And so we have to, all you got to know is what is CV, and we are fine. So to find the CV, we can go to test and go to property tables and look for the PG model. The gas models are here. And if I, in the PG model row, if I click on common gases, I should find hydrogen property. Of course, hydrogen molar mass is given here. I assumed it to be 2, which is, everybody knows that. And I could pick up R, but notice instead of using R, I personally prefer to use R bar over M bar as the value of R. That way it reduces using, looking up a table. If you just know the molar mass, you can find R, the gas constant. So if I continue here, you can find CV. CV is about 10 point, I'll say it's 10.2 approximately. So if I pick that number. 1 is my mass, 10.2 is CV, and T2 minus T1 is 200 minus 20. Note that I picked up the Celsius. I substituted temperature in Celsius. Of course, Kelvin and Celsius are linearly, shifted. If I added 273 to T2 and T1, I'll have no difference. I'll have the same value here. So it turns out to be about 1836 kilojoule. Finally, to find the change in entropy, we notice that there are two formulas for specific entropy. One is mCv ln T2 over T1 minus R ln, and the other one is mCp ln T2 over T1 minus R ln P2 over P1. Obviously, which one should we use? Because the volume remains constant, mass remains constant, we recognize then the volume ratio equals 1, and therefore the log of that goes to 0. So this is the first one, is a simpler formula. So if I use that, I'll get 1 is the mass, CV is 10.2, and log of 473 by 293. Notice that now I cannot use Celsius anymore, and that gives us approximately 4.885 kilojoule per, oops, there's no multiplied by mass already, so kilojoule per Kelvin. Okay, so we found the solution manually. This is the change in pressure. So let's go verify the solution first. To verify the solution, we go to thermofluids.net. I already logged into another tab here, and we go to the TESTcalc modules, and the question is, you see a lot of choices here. Of course, if you hover the pointer, if you just park the pointer somewhere, and it will come up with the help of what it means, that branch means. And of course, it follows the thermodynamic logic. Instead of doing a system analysis, let's just attack the problem as a state analysis problem. That is, we are just trying to find the properties. What is stored energy at state 1? What is stored energy at state 2? What is the change in entropy? So therefore, these are just evaluating properties. Which kind of state should we choose? Of course, a system state, because as you can understand, a fixed volume of the system is given, a closed tank, so that's the best one. Flow states, we go only for a flow. If you want to find the state of a flow somewhere, say at the inlet of a turbine or exit of a turbine, etc. So we go to the system state TESTcalc page, and we find a lot of different models. Of course, in this particular problem, the problem asks us to use the PG model. There are several gas models, so we'll choose the PG model. Once we choose, actually it comes with the animation tab. Of course, there are some examples here. There's a discussion tab here. You can post a question or whatever you want. And this is the TESTcalc page. And if it doesn't start running like this, that means you don't have Java installed. Sometime in Firefox, you have to click on this Lego button, and you have to say Java plugin. Even if you have Java installed, you have to say allow and remember. Okay, so going back to the verification of the problem, this is the TESTcalc. So we'll simply select the gas, which is hydrogen in this case. And state 1, this is the state panel. And in this state panel, which is the state panel is basically a collection of properties. And you notice that the properties are color-coded. The thermodynamic properties are, this is the description of the state here. The thermodynamic properties are in blue color. The material properties are in red color, and extrinsic and extensive properties are in green and black respectively. Anyways, So let's go ahead and calculate state 1. So how do you turn on a property? How do you enter a property? You click on this checkbox that puts it into an input mode. The temperature is known to be 20 degrees Celsius. So you choose the unit. Also, what is known is the mass, 1 kg, and volume is 2 meter cube. Notice the properties are calculated. All the other properties are calculated. We go to state 2, and you can go back and forth between states like this, or you can directly pick a state like that. For state 2, what we know again is temperature is 200 degrees Celsius is already chosen. We know mass doesn't change and volume doesn't change. Okay, so therefore the state 2 has been completely calculated. We can go to the I/O panel and pick up what is P2 minus P1, and that's 371. If you recall, what we calculated manually was 374. As far as engineering is concerned, that's pretty close. How do we find the change in stored energy? Well, that's M1, mass doesn't change, times E2 minus E1. That's the specific stored energy. So the change in stored energy of the system will be this, which is 1832. And what did we get? 1832. Ours was 1836. So that's a pretty close answer. Percent-wise, the difference is very little. How about the entropy change? M1 star, change in specific entropy, small s2 minus s1, and that's 4.87. Again, this answer is, I think our answer was 4.88. So very, very close answer. So as you can see, a TESTcalc can very easily verify a solution. Now suppose the question is, how will the answer change if the gas was CO2? Notice how simple it is. All you do is to go select CO2 and click the super calculate button, and all the computations are updated. Now you can come back here and you can say, oh, P2 minus P1 is only 17 kPa this time. So all the answers you can recalculate. There are many other features of TESTcalc. I don't want to go in there, but finding a state is really easy. You essentially enter the properties that are known and hit the enter button or click the calculate button to calculate the values of all the other properties. Calculated states can be also plotted on a, say, a TS diagram, and you can make sure, look at the visual verification. You know the volume remains constant, so if you draw a constant volume line, it should go through state 1 and 2, and that gives you confidence in your calculations that you didn't make a big blunder. Okay, so now that we know how to solve the problem manually and verify, let's go make sure that we did it correctly. How do you check and how do you keep a record of every problem you have solved? Well, now that we know the solution, we can go, this is a problem from this test website, so we can go find the problem number 346. So for that, we go back to thermofluids.net, and let's go this time to the problems module. Go to, we could search the problem right here, but we can go to the chapter 3, and look at the problem number. It is problem number 346, which means chapter 3, section 4. We can click on section 4, which is all gas, PG and IG model problem, and we can, scroll down and you find 346. You'll notice several things in this problems module. This figure is connected to the animation. If I click there, it will bring up a relevant animation to explain the problem to us. Clicking the picture again will close the animation. Of course, even the solution is given, but obviously not for students. The solution is only given to people with special permissions, like your professor, for instance, or professionals who have the correct privilege. Now, but however, if you cannot solve the problem, you can always click the discuss button, and you can find what other people have made comments. They may have put some hints there. or you can ask a question, and someone, I'm pretty sure, will help you out with some hints. Okay, so now how do I know if we have solved the problem correctly? For that, you just click on the problem number, and that brings up a dialog box, and there it tells you that you have not yet attempted the problem. Number of attempts is 0. So suppose I arbitrarily put some number here as answer, and it will say, uh-oh, these answers are incorrect, and your number of attempts are going up. Okay, so these are only part A and B, which is about, what is part A and B? Pressure and stored energy. What are the answers we got for pressure? Remember, we got 374, I believe. So let's enter 374. And if I grade my answer, look, that's correct. What about the change in stored energy? I believe we got about 1836. I wrote it down somewhere. 1836 kilojoule. And look, both are correct. And when I correctly answer a problem, the problem number gets a green background. So in other words, from now on, if I log in next time, I will always see the problem that I have solved in green background. If I cannot solve a problem, of course, it will come in with red background if I try something. And you'll also see a lot of symbols up here. When you see a key, if you click on the key button, the thing is that in addition to the dialog box for entering the answers, it also gives you some hints if you cannot solve the problem. You can click and you can say, show me some, I could use some hints, then it will give you some hints. Those are called key problems. And there are many other features, like you can go and see, go to the progress report and see how many problems you have solved so far, and what's your condition now, or outcome based learning, like which problem helps you learn what objective of thermodynamics. These are called learning outcome, and these are numbered here. So each problem you solve will add your bar chart, and you want to make sure that you have all these outcomes covered if you want to be a really good analyst in thermodynamics. Well, it's getting a bit too long, so I'll stop here, but you can see the potential for how test can be used to verify a manual solution. And then once you verify the manual solution using TESTcalc, you can go click on the problem number in the problems module and record your answer. So next time when you come back to the chapter, you will know that you have already solved that problem, and you can go solve a different problem next time. Also, you have seen how can you study what if scenario. We just studied just one situation, that what if hydrogen is changed to carbon dioxide. But you can imagine you can change any variable, and you do so much more. And finally, one thing I forgot to mention, that when you click the super calculate button, it produces a detailed output. And not just that, the details output that it produces also contains something called the TESTcalc. The test code. You can copy and paste this code, and later on you can copy and paste it in a word processor and save this code, and later on you can come back to this TESTcalc and paste it in this IO panel and click this load button, and that is it. The moment you click the load button, your entire solution will be again loaded into this TESTcalc. In other words, you don't have to go through the drudgery of entering every variable in this spreadsheet, in this visual spreadsheet. So imagine a problem which involves, say, 20 different states, and yes, there are problems like that. So then this TESTcalc, the test code becomes quite handy, which you generate by clicking the super calculate button, and you find it here along with all the details output. You can see start of test code here, end of test code. So this snippet of code, if you just save it in a word processor in your computer, later on it will serve you to regenerate the solution instantly. Okay, I'll stop here, and I will use this solution as a launch pad to show that now that we know how to solve finding properties of states, how we can leverage that to solve even more complicated problem in future video examples. Thank you for listening, and happy problem solving.